Hi, I'm Maya. I'm in Mr. Austin's ACME class, and I'm going to be talking about shooting stars. So I want you to think about what a shooting star is and what you picture when you think of a shooting star. Where it is or what it looks like, and maybe what you've seen from pictures or videos, or even if you've seen one in person. But now I want you to think about what really is a shooting star. Do you know what it's made up of, or where they come from, or why they exist in the first place? And if you don't, that's okay, because I'm going to explain all of that in my presentation. So shooting stars actually have nothing to do with stars or constellations. They're actually these objects from space called meteoroids, which are tiny bits of dust and rock that fall into the Earth's atmosphere. And as you can see, shooting stars are not just the object, but there's a trail of light that follows it. Those are called meteors. And then the last term I want to share is when a meteoroid comes into Earth's atmosphere. It usually burns up, or it can make impact with the Earth. And when that happens, it's called a meteorite, which are usually large meteoroids, but they're pretty rare. So there is a history to shooting stars or meteoroids. This on the left is a sketch of an early meteor shower, which I'm going to talk about in a little bit, from 1833. So the largest meteorite recorded to scientists, it happened in southern Nebraska in 1948. It was 2,360 pounds, and it went 10 feet deep into the ground. And then this picture on the right is the largest crater. This is the meteor crater in Arizona, and it's said to occur some 20 to 50,000 years ago. It's a whole mile wide, and this one is 600 feet deep, so pretty large. The next thing I want to talk about is, where do shooting stars come from? So like I said, they come from space, but they don't just come from thin air. They occur when Earth passes through a trail of debris from a comet as it orbits the sun. So when a comet orbits the sun, it starts to melt, and tiny bits of rock or chunks of rock or dust come out of the comet, and the Earth intercepts with this debris. And these are just some diagrams of what happens. So you can see there's the sun and the comet's orbit and the Earth's orbit, and then as the Earth's orbit travels this way, it intercepts with all this debris, which is why it comes into the Earth's atmosphere. There are some well-known meteor showers that I'm going to talk about really fast. So scientists, what they do to distinguish different meteor showers is they name them based on the constellation where it looks like the meteor shower is coming from. So this first one is called Leonid, after the constellation Leo. It occurs every November, but it's most beautiful every 33 years. That's what scientists think. So this next meteor shower is called Perseids. It occurs every August. It's considered to be the most widely watched meteor shower, and it comes from the comet called Swift-Tuttle, which orbits the sun every 133 years. This last meteor shower is called Orionid, after the constellation Orion. It occurs every October, but within that month it can last up to a week, which is pretty cool. And at its peak, there are 50 to 70 shooting stars per hour. So this one comes from Halley's Comet, which orbits the sun every 75 to 76 years. So that's just a little bit about shooting stars. I hope you learned something new, and thanks for listening.
Hi everyone, I'm Mitch, and today I'm going to talk about antimatter for a little bit. So antimatter at first sounds like a really big and scary and sciencey topic, but I'm going to try and simplify it down to chocolate and vanilla cookies. So first, let's define some terms. Let's talk about first what matter is. Matter is just stuff. Matter is all the stuff in the universe. So whether it's contact, case, or apple, it's all made out of matter. Matter is at its simplest form atoms. And really, there are other things making up atoms, but atoms are what we're going to think of as the building blocks of matter, the smallest piece. Now let's take a second to figure out how small atoms actually are. If you take an object kind of like the size of an apple, and then you took each atom in that object and made it bigger to be the size of something still small like a blueberry, that apple would now be the size of the entire Earth. That's how many atoms are in a regular apple. Now each atom also has a certain quality to it called charge. A charge can either be positive, negative, or neutral, but really you can kind of think of it like a color. For instance, this apple is green, or my shirt is purple. Some atoms are negative, some atoms are positive, and some atoms are neutral. That really controls various other interactions between atoms and with atoms and other things, but for now you can just think of it as a color. The last thing I want to define is energy. Our common definition of energy is something kind of like battery life. Your phone needs a lot of battery life to be able to do things. You can't take pictures or play games or text people if you have no battery on your phone. Well, similarly, in the physics definition, you can't move an object or heat an object up if you have no energy. So for instance, if I have this pen right here, and I want to move this pen, I need energy to move it. I need to move my fist, which means I have energy in my fist right here to move the pen. Or if I'm under a really hot lamp, all the light from that lamp, the light energy, is heating me up. So now let's talk about what antimatter actually is. Antimatter is really just the exact same thing as regular matter. The only difference is that it has an opposite charge. So as I said, it's like that quality. If regular matter has a positive charge, the antimatter version of that has a negative charge, and vice versa. The other thing is that when antimatter and regular matter touch, they annihilate and they give off energy. So now is how I want to talk about cookies as antimatter. So if you think of, for instance, a regular bakery that makes a lot of chocolate cookies, let's think of these chocolate cookies as matter. This bakery uses these chocolate cookies as the most basic ingredient to their other big productions. You know, they can make chocolate ice cream cookies, they can make double-decker chocolate cookies, they can do anything with them, but they always start out with a chocolate cookie. Let's take another bakery in a totally different city that only makes vanilla cookies. It can do the same thing. It can make vanilla ice cream cookies, it can make double-decker vanilla cookies, it can make chocolate chip vanilla cookies, it can do whatever with them. But the entire thing is that it's a different flavor cookie. Well, that's really how matter and antimatter are. They're just two totally separate versions of the exact same thing. They have one different quality. One is vanilla, one is chocolate. Of course, for whatever reason, with matter and antimatter, when they touch, they just destroy each other. They get annihilated. And what happens when they touch each other? A little bit of energy pops up. That just means a little flash of light, and then it goes away forever, and then they're just not there anymore. So you probably have a lot of questions about what I just said. For instance, where is all the antimatter? Because if it were here, wouldn't it be touching all the matter around us and being destroyed? Well, the answer to that is when the universe was created, a lot of antimatter was created and a lot of matter was created, but slightly more matter was created. So that means all the antimatter paired with matter and destroyed each other, but then there was still some matter left over. To demonstrate that, imagine this is the beginning of the universe. Imagine the chocolate is regular matter and the vanilla is antimatter. Since there's a little more chocolate, here's what's going to happen. These two particles, they're going to touch and both get destroyed. These two particles, they're also going to touch and both get destroyed. Now, there's no antimatter left and there's a little bit of matter left. This matter is what we think of as our universe today. You might also be wondering how exactly we know all of this. Like, how do we know that they destroy each other if there is none of it left? Well, the really cool thing is that scientists have actually made antimatter. They did this in a place called CERN. This is this giant lab in Europe. And they store it with these magnets, these really giant and complicated magnets that make it so the antimatter doesn't actually touch anything, not even air, because it would still destroy itself if it touched air. So they made antihydrogen, which is, if you've heard of it, hydrogen is a type of atom. Antihydrogen, again, is just that same type of atom except with an opposite charge. And they know that it's this exact same as regular matter because they've measured the light of this hydrogen atom and they measured the light of the antihydrogen atom, and it's the exact same. And so it's really cool, but the truth is, physicists really don't know a lot. They don't know why there are different amounts of matter and antimatter at the beginning of the universe. because according to all the leading theories right now, there should have been the exact same amount of matter and antimatter created. Nobody knows why there are different amounts. There are a lot of other mysteries regarding antimatter, but for now, scientists are working with what we do know. So, in fact, scientists have actually used what we do know about antimatter to work on the imaging and the treatment of cancer. They've also used it to theorize about making fuel for rockets and cars and everything. Some people have even thought about making weapons with antimatter, but thankfully that's proved pretty much unsuccessful so far.
Hi, my name is Vicky and I'll be talking about what we can't see. So there's a lot of things we can't see, so I'm going to just give a few examples. So first off, stereoneutrinos. So stereoneutrinos are just like regular neutrinos. They're massive matter particles that do not carry any electric charge. But the difference is that they don't carry any charge at all for any force, unlike neutrinos, which is why they're called sterile. They're free from any influence of any other forces. Now, infrared radiation. So, infrared was discovered by William Herschel. He ran an experiment where he put thermometers measuring the temperature of the different colors. And he saw that from blue to red, the temperature increased. And so he realized that every object has infrared. But to us, we may not be able to see the infrared waves. So we can't see the infrared waves coming from humans or from animals, but we can see the infrared waves of fire. So we have to use other special instruments. So in this case, there's thermal imaging, where we can see the heat of this dog. Now, X-ray. So most people think of X-ray when they've broken a bone or may have broken a bone, and a doctor needs to see how the bone is. But X-ray is also in astronomy. So first off, what is X-ray? So X-ray is electromagnetic radiation, which is transmitted in waves or particles at different wavelengths and frequencies. And so X-ray in astronomy can be found in celestial sources, in closed binary systems, or neutron stars. There are additionally black massive holes at the centers of spiral galaxies, which can emit X-rays as they absorb stars. Okay, so now gravitational lensing with dark matter. So first off, what makes up the universe? This chart shows what makes up the universe. As you can see, 4% makes up the universe of normal matter. And so normal matter would just be a planet or a star. And so in this case, mass and energy equal each other. And so mass is just a measurement of the internal energy content of an object. So dark matter and dark energy is what we know is there, but we can't see, which is why we call it dark matter and dark energy. And so as you can see, it makes up most of our universe, but we can't see it. So we can use gravitational lensing. So gravitational lensing works just like a magnifying glass, but mass is what bends the light. And what happens is that the gravitational field of a massive object will extend into far space, as you can see in this image. And the light rays passing close to that object bend and refocus somewhere else. And so gravitational lensing is useful to cosmologists because it's directly sensitive to the amount and distribution of dark matter. Now, gravitational waves. So we've known about gravitational waves for a really long time. The scientist Albert Einstein came up with a lot of ideas on gravity and space. And one of those ideas was that when two bodies, such as planets or stars, orbit each other, something special would happen. And the special thing would be ripples in space. And these ripples are just like when you throw a pebble into a pond. And these ripples in space started being called gravitational waves. And gravitational waves are invisible, and they're incredibly fast. They travel as fast as light, which is 186,000 miles per second, which is really fast. So here are just a few examples that we've discovered using special instruments. Thank you.
This is a black hole, one of the universe's greatest mysteries. A black hole can be thought of like an interstellar vacuum. With some black holes weighing up to billions of times the mass of our own sun, these monsters have so much gravity that even light can't escape from it. It's completely invisible to the eye as it reflects no light, and if you were to float by it by accident, you'd be sucked in and never seen again. How are these things created? Black holes are created from stars, ones much, much bigger than our own sun. A star is kept in what's known as dynamic equilibrium during its life cycle. Matter is drawn towards the center of the star due to its own gravity, but the star is kept from collapsing due to the thermonuclear fusion that happens in the core. Once the star's energy source depletes in the middle, the gravity overwhelms the star and the star collapses in on itself. Sometimes this can result in a neutron star, an incredibly dense star. Or it can turn into a supernova, a massive explosion that sends all the matter of that star flying out into the universe. Or in some cases, it can turn into a black hole, where all the matter condenses into one small point. It's impossible to talk about black holes without first mentioning Einstein's theory of relativity. In 1915, Einstein attempted to understand gravity and how it works in the universe. He proposed that the curvature of space-time is directly related to mass, momentum, and the energy of matter and radiation in our very own universe. Einstein also said that the defining property of a black hole, the greatest sum of mass and gravity in our universe, is protected by an event horizon. The event horizon is the point of a black hole, which is known as the point of no return. Once you cross the event horizon, you're no longer able to escape the gravity of the black hole, and you're eventually pulled towards the middle of it. The singularity, or the point with the highest density in the middle of the black hole, is only allowed to exist with this event horizon, the point of no return, because the event horizon acts like a cloak, hiding the singularity from our vision. So if black holes continue to suck in all the matter of the universe, with none of it being able to escape, where does it all go? And this is where the theory of black holes leads to the theory of white holes. White holes exist as the polar opposites of black holes. They expel light and matter, and they push matter away instead of sucking it in like a black hole would. As matter falls into a black hole, it would appear to an observer to take an infinite amount of time to cross the event horizon, as the gravitational pull is so strong it can theoretically stop time. In a white hole, the matter being shot out has been skewing past the event horizon for inversely an infinite amount of time, technically allowing you to see into the infinite past, as the matter that is getting out of it has taken an infinite amount of time to cross that same point. As you approach a black hole, gravity forces you to accelerate towards the black hole, making it harder to escape its grasp. If you tried to approach a white hole, however, from the outside, it would be harder the closer you got to the singularity. The acceleration needed to enter it would be incredible, and not even all the energy in the universe combined would allow you to get inside of one. In this sense, white holes and black holes create what's known as an Einstein-Rosen bridge, or more commonly referred to as a wormhole. Matter that's collected by the black hole in one universe is transferred across the threshold of space and time and spewed into another universe through the white hole, and in some cases, maybe even creating an entirely new universe in the same process. Many scientists, including Nikodem Pawlowski at Indiana University, who created this theory to begin with, thinks that the Big Bang, or the explosion that created our universe at the beginning of our time, was actually a white hole releasing all the matter, light, and energy its counterpart black hole collected over its lifespan. In the 1970s, theoretical physicist Stephen Hawking calculated that all black holes should evaporate mass by emitting radiation. When black holes lose more mass than they gain, they simply become smaller and eventually disappear from the universe entirely. However, some scientists don't believe in that, and they now think that a black hole cannot just simply disappear, as this might damage the space-time fabric. From this line of thinking, those scientists believe that when black holes lose all of their mass and disappear to one really small point, the now black hole will rebound into a white hole, spewing all of the mass it once sucked in back out into the universe. As you can see, white holes are just a theory with many different lines of thinking attached to it. but delving into this theory might help us explain how our universe came to be and how we are where we are right now.
Hi, I'm Myles, and today we're going to be discussing large quasar groups. To understand what that is, first we need to understand what a quasar is. A quasar was first discovered in the 1950s when astronomers found a very small and very bright object deep in space. They weren't sure what this object was because unlike any planet or star they had ever seen. They called it a quasi-stellar object, quasi meaning fake or similar to a stellar object. There are many theories that surrounded quasars when they were first discovered. Some suggested that our entire understanding of the universe and its expansion was misinformed, and others, more out there, suggested that extraterrestrial civilizations were harvesting stars for energy. In the 1980s, a more solid theory was established called the active galaxy theory. In all galaxies, including our own, there's a supermassive black hole at the center. As material gets really close to the black hole, they form things called accretion disks. The black hole will then heat these accretion disks up to millions of degrees and jut them out in a jet of energy, as you can see here. Due to the black hole's magnetic properties, there will be two jets of energy in either direction that will continue on for millions of light years. These jets will continue until the black hole runs out of material to consume. Think of it like a fire. The fire will eventually die out if there's no more material to burn in it. Suggests that even our galaxy, the Milky Way, once had a quasar at the center, but then over time the black hole ran out of material to burn up and then simmered down and became a non-active black hole. What black holes with quasars are called galactic nuclei. Many galaxies, not other than our own, have active galactic nuclei, and in about 4 million years, our galaxy might have a quasar as well. It's because in 4 million years, the Milky Way galaxy is expected to collide with the Andromeda galaxy, creating a super massive quasar. So now we need to get into something called the cosmology principle. And the cosmological principle suggests that if the universe is cut up into a bunch of even pieces, all those pieces will have about the same amount of matter in them. Here we have 3 circles of the universe, and according to the cosmological principle, all these circles will have roughly the same amount of matter in them. However, here's where it gets complicated. Quasars often travel in groups, and large groups of quasars are expected to exceed this principle and prove it wrong, which has become a real heat of confusion to scientists. And cosmological principle showed that no part in the universe could be more than 500 million light years large, and scientists relied on this theory for predicting where matter would and wouldn't be. This was all good up until the 1990s, when a group of quasars was discovered. This group was incredibly large and gained the term large quasar group. It was about 2 billion light years large, which contradicted the cosmological principle. This led to a lot of controversy and much reevaluation of our understanding of just the scale of the universe and how it is. However, 2 billion was not big enough to completely prove the theory wrong, and things continued on all well and good up until about 2013. In 2013, a large quasar group was discovered that was bigger than anything we had ever seen. This object was considered the biggest in the universe and has even brought up to question some of our basic laws of physics. They define this as the huge large quasar group. This huge large quasar group had 73 different quasars in it and took up 9 billion light years. This is far more than the 500 million that the principle predicted, and it really brought into question a lot of solid theories. So what does the huge large quasar group mean for us? It means the universe might not be exactly as it seems, and some of our physics, our preconceived notions, and all our discoveries could be in question. So That being said, the discovery of the huge large quasar group was relatively recent, and all the data on it still needs to be analyzed and put into perspective. But this is the largest thing in the universe, and it has been very incredible to see. Thank you, and I appreciate your time.
Alright, so now we're going to talk about string theory, but before I do that, I'm going to give a little overview of fundamental particles. So, all matter in the universe is made up of atoms, and those atoms are made up of electrons, protons, and neutrons. And the protons and neutrons are made up of even smaller particles called quarks. And the quarks and electrons are currently what scientists think are the smallest things ever. So they're known as fundamental particles. But string theory says that these fundamental particles are actually just little points, and in those points are strings. They're like little flat lines that can either be straight or they can be curved and make a loop of string. And each individual string has a frequency that it vibrates at. And depending on the frequency that it vibrates at, that determines what type of particle it appears as, and how heavy it is, what kind of charge it has. It determines all the different things about it. But for this theory to be accurate of all the strings being everywhere, scientists need to assume that there are, instead of 3 dimensions, humans can move in 3 dimensions. Forward, backward, left, right, up, down, x, y, and z x's, as they're called. And we can observe the 4th dimension, but not interact with it, because that's time, and we can't travel through time, at least not yet. But for this to be accurate, scientists need to assume that there are 11 different dimensions, and we don't know what they are. But without these dimensions, we can't assume that string theory is real, because the strings need to be somewhere, and a lot of scientists believe that they're just coming through from other dimensions into our dimension. However, compactification is something that helps make it a little simpler. A good example of compactification is if you take a pen. If you look at it closely, you can see that it has an up, down, and left and right. It has space in both of those directions. But if you get it far away enough, you can't really see that it goes left and right anymore. It looks like it's just a line that goes up and down. So in this way, an object with 2 or 3 dimensions can appear from far enough away or from different enough sizes, like it only has 1 dimension. And a lot of scientists believe that this is one of our primary issues when dealing with the 11 dimensions of string theory. Compactification basically says that these dimensions can loop back on each other and close up and sort of interweave, like this example here. And M theory, which is the current accepted version of string theory, it's interesting. Originally, string theory was all over the place, but a bunch of different groups of people had different ideas of how they thought string theory worked. And over time, people saw that they were different ideas, but none of them were wrong, and they were connected. So eventually they all came together and connected the individual theories, and it was condensed into what's called M theory. And M theory helps keep all the information contained and make sure everyone's using the same idea of string theory so that everyone can make the progress together.
Hi, my name is David Rothman, and I'm going to be talking about special relativity. Now, special relativity is a scientific theory that was published in 1905 by this guy, Albert Einstein. It posits that the speed of light will always be the same, no matter the direction or speed of the person who is measuring it. It also implies that space and time are connected in a way that was never thought about before this theory was published. Now, light moves at a constant speed. We know that, that's what the theory suggests. However, it also moves at a constant speed no matter the source. So if you've got a flashlight, you click it on, you move it around, move it back and forth, it's always going to remain the same speed. This is strange because this isn't how matter works, usually. Let's say you've got a ball and you drop it from a standing position, like this red ball. You drop it, it goes straight down, nothing else. However, if you're running or if you drive a car and then you drop the ball will go down, yes, but it will also go to the direction that you were running, driving the car, etc. It'll go follow that path if you were running in that direction. Now, there's some vocab to cover before we move on. So one of the things that we have to cover are reference frames, which are how we experience the universe. You have a different reference frame than me, as do your teachers, parents, friends, etc. Everyone has a different reference frame. Another thing that we have to cover is the change in which we experience time. That is called time dilation. We'll get to that later. Along with the change in the way we experience space, which is called length contraction. We'll talk about both of those things later. The last term that I want to define is simultaneity, which means two things that happen at the same time. Now, special relativity is based around two assumptions called postulates. The first postulate of special relativity is that there is no absolute reference frame. There is no place or time or anything that you can go to that is uniform and that will give you all the objective answers. The other part of that postulate is that the laws of physics are the same throughout all inertial reference frames. An inertial reference frame is a frame of reference that is not accelerating. Now, the thing with this is that no one can truly distinguish between reference frames, so it can kind of mean anything, any reference frame. Because, let's say you're moving in a car, like that car. You don't really know if you are just sitting down and staying still while that building whizzes by you, or if you are moving while the building stays still. Due to that, the physics will always play out in the same way. Now, the second postulate of special relativity is that the speed of light in a vacuum is the same for all observers. Now, the usual equation of speed times time equals distance gets a bit wonky when it comes to light because speed is always constant. So that means that the only variables that can change are time, which is time dilation, like we talked about, and distance, which is called length contraction, again, like we talked about. But I'm about to go into it a little deeper here. Time dilation occurs when another reference frame is moving relative to you, and time in that reference frame slows down compared to you. So, let's say you were moving at a certain amount of speed, like 100 miles an hour around a racetrack, and your friend was sitting down in one of the seats. You would experience time moving slower than your friend would. It's weird, but it would only be a little bit. Another thing to consider with this is that there's no universal concept of simultaneity, the term that we defined earlier. In other words, what you think happens at the same time might not be happening at the same time to another person. So let's say that there are two lightning strikes. Let's talk about these two. Now, you are right there. You are right in the middle of them. And what happens is they both strike and you experience them at the same time. You see the light at the exact same time, and you think to yourself, those two lightning strikes happened at the same time. However, let's say your friend was right there, closer to this lightning strike right here. They would see first this lightning strike, and then this lightning strike, because the speed of light is constant, and it won't speed up. So, in their reference frame, they will see this lightning strike hit first, and then this lightning strike at a later point. So, to your friend, lightning struck one end earlier, even though it seems simultaneous to you. Now, what happens with length contraction is that an object moving past another observer appears shorter than it would be if the object was just staying still. So, let's say you are on the corner of Clark and Webster, and this car comes whizzing by right down Clark. Now, if it was standing still, it would be approximately 10 feet long. However, when it's moving away from you, you observe it as a tiny bit shorter. Now, of course, in both of these instances, the amount of time that is crunched, the amount of time that is, I guess, squished, and the amount of space that is also squished is so small that we don't consider it a part of our intuitive sense of physics. However, to put it into reference, that car driving down Clark, it would be a fraction of an atom's length shorter when it's driving away from you. However, it's still just that tiny bit shorter. However, special relativity says that because light always moves at the same speed, time and distance change to compensate. That is both of those examples that I just gave. That is the direct connection between space and time, hence the term space-time. A good way to visualize this is to imagine a three-dimensional cube moving. So let's say this cube was moving like this. It was moving this way. That would be the time dimension. You've got the height, you've got the width, you've got the length going back, and it entirely is moving through time. That is the best way to describe it because it is, again, a fourth dimension. Well, it looks like that is all the time that we have for now, but if you want to hear more, just come and see our presentation. Thank you.